Alright, so we're doing lesson 4 here. Lesson 4, and this only has 2 objectives in it, and they're pretty important. Sort of short, but pretty important. First of all is write the mechanism of an isolated diene, of the electrophilic addition to an isolated diene. I'm going to argue that that's just a review of what's on page 238. Page 238. We're really page 365 in chapter 8, but this is a review of that, okay? And I do have a video for electrophilic addition. Please look up under the videos for mechanisms, electrophilic addition. I think it's -HX is the video for that, and we'll talk about that in a second. The second objective is write the mechanism for the electrophilic addition to conjugated dienes. This is really what this is about. This lesson is mostly about objective number 2. Okay? Get this term in your head, kinetic versus thermodynamic control. Pretty scary, those 2 terms are, but I think we can demystify those a little bit. On page 370, there's a magic picture. I really want to emphasize that picture on page 370. It's an energy diagram. If you're not super comfortable with energy diagrams, it may be a little bit scary, but we really need those pictures. So we'll have to get comfortable with those. All right. So let's go on. Objective number 1, lesson 4. Objective number 1 is write the mechanism for an isolated diene. I am going to do that just because it's so useful. So there's an isolated diene. Why is this an isolated diene? Isolated diene. Why is it an isolated diene? Does that just sound like jargon? Am I just throwing words at you when I say that? You can see why it's a diene, right? And can you see why it's isolated? That's a term I've never used before. Well, what do we mean by that? Well, what's the hybridization of that carbon right there? Every time I ask this, I see Becca say sp3. And others do too, I know, but I've just noticed. Okay, every time I ask the hybridization of that, I see several people say sp2. That's sp2. Okay? Can you see how you do not have an uninterrupted system of pi electrons? You do not. Right? Here. Okay? So that's what we mean by isolated. Okay. Now, if we take that and treat this with HX, this is going to look a lot like my video for electrophilic addition, HX. We're going to get pi electrons that come and attack that. Boom, boom. Okay? Oops, sorry, that's not there. The hydrogen either goes there or it goes here. Right? Now we ask ourselves, which of these is better? Which of these is better? This is better because it's got 2 alkyl groups on it. There's an alkyl group and there's an alkyl group, right? And a Hammond postulate says that alkyl groups are electron donating. Alkyl groups are electron donating. This guy only has 1. This carbocation only has 1 alkyl group, so this one's better. It's got 2. We did that in lesson 3. Okay. So I'm going to put a big X through that. On test day, I'm probably going to draw both of them out and then evaluate those. That is when I'm under pressure, right? I'm going to draw both of them out, then decide which one's better instead of just memorizing it. So the next step is, boom, right? Okay, and that goes to that. All right? I didn't leave myself enough room there. All right, and so the rest of this section here, isolated dienes, it's roughly on page 365. Not roughly, it's exactly on page 365. The rest of that shows you that if you've got another mole of HX or another equivalent of HX, then you can also add to that one too. Okay? So let me leave that off. That's objective number 1, lesson 4. Okay, objective 2, lesson 4. All right, running out of scrap paper here. is, here's the magic one, I'm telling you. Right, the first one is write the mechanism of an isolated diene with HX. And you want to evaluate the energy diagram too, which I did not do for this. I'll do that tomorrow in class. Or not, if no one asked me to. But this one's the big one. Objective 2, write the conjugated diene HX, and we're going to see. I haven't said anything about this yet, but hopefully you've already read the book on that. All right, so let's talk about that. All right, you're going to see some magic. This is one, in my opinion, one of the best looking, one of the coolest mechanisms that we'll do all semester. So let's take this and talk about the electrophilic addition to a conjugated diene. All right. So there's a couple possibilities here. I'm going to consider them all independently. We've got pi electrons that attack that. Yeah, of course. And if that attacks that, that goes there. Or it could be that over here. All right. I'm going to consider them separately, 1 and 2. So let's consider situation 1. In situation 1, we're going to get right, for reasons which we just described in the previous one, we know we can discard this. That's a primary. So this is what we're going to get. Right? Can you see what happened? These electrons attacked that hydrogen and left one of these carbons as a carbocation. Which one? Well, the one that's got more alkyl groups on it, okay? So then what happens is the X comes in, which we got from here. There's my X minus, right? Because the electrons go there and make an X minus. These electrons come and go, boom, right? I'm considering 2 possibilities up here. I'll talk about the other one in a minute. But this is step 1. All right, now watch this, but there's something else that could happen. This could go there also. Right, so I've already got 1 and 2 up here. Let's consider this, say, root 3 and this root 4. Root 3 is going to go here. Right? Root 4, though, is going to go here. Agreed? Okay, and if that's the case, that's 4. Here's 3. You can see this is pretty elaborate. You may need to watch this video a couple times. And of course, we'll do it again in class. But that's root 4. And then, of course, also here's the other possibility, which is going to give us, or not the other possibility, the last step is going to give us that. Okay? There's a final product, and there's a final product, right? We still have other possible. There's a final product of if we follow 1, and then we've got 2 possibilities there. That could go there, or it could go here. This is all in your book, by the way. So if this is confusing, first of all, I'm going to tell you, yes, I know. It's very elaborate. All right, we considered possibility 1. Let's consider possibility 2 now. Okay? I've done this a couple times. I now remember, oh, both of these are going to give me secondary carbocations, plus this. Right? It's either going to go, the hydrogen's either going to go here and leave a carbocation here, or it's going to go here and leave a carbocation here. Which of these is better? Aha, that one's better because it's allylic. You see that's an allylic carbocation? We did that. That's allylic carbocation. We did that in lesson 3, one of the lesson 3 videos. I don't remember which one. Okay, so this is the primary one. This is fine because it's secondary, but allylic is much better. Allylic is roughly equivalent to a tertiary carbocation in terms of energy. So I'm going to put a big X through this and say this is what we've got going on. Now we've got the X minus, right? Either that's going to attack here, boom, or that's going to go there. Right? So let's consider those as 2 possibilities, 2 separate possibilities. I've already used 1, 2, 3, and 4. Let's call this 5, and that's 6. Okay, if 5 goes, what's that going to give us, and what happens if 6 goes? All right, let me leave that as an open question. Maybe you please consider pausing the video and predicting what 5, this is 5, and this is 6. Okay? Now, that's an explanation, that is, I think, an explanation of what happens to conjugated dienes. Now let's consider the ramifications. Looks like I've got some junk from some previous conversations here. Let's go here. Okay, I'm going to go through the whole thing again. This time I'm going to go with a simpler story. Let's just consider 1,3-butadiene. Okay, if this goes with HX, we're going to get that. All right, these are both the same, so I'm just going to choose the second one here. And you're going to get a carbocation there. Right? Boom. And that's going to go there. Okay, that's one possibility. But I'm going to call that step possibility 1. Possibility 2, though, is that those pi electrons could come over here and go right and give a primary carbocation. Agreed? Look at that. Now, X would come and hit that, and we would result in boom, boom, boom. That and that. Okay? Now we can see where the terms come from. If this is carbon 1 and that's carbon 2 and that's 3 and that's 4, this is a 1,2 addition. This is a, we got an addition to the 1. I didn't draw the hydrogen in this time, but that's where the hydrogen went. Perfect, let's draw it in. Right? The first hydrogen, that goes to carbon 1. That's where that comes from. Look at that. You might need to do some accounting. Go back through and see where things come from. This is a 1,4 addition. Alright? So page 370 tells you why well, under some conditions we get 1,2 addition, and under other conditions we get 1,4. I'll give you a lead-in, even though I'm not really teaching when I tell you this, I guess. This is called kinetic control. This is called thermodynamic control. You know, I'm going to tell you now. I wasn't going to tell you. This is called kinetic control because it's faster. But I'm going to let you prove it to yourself by looking at that magic picture on page 370. The magic picture. As my wife would say. The magic picture. Kinetic is faster. And thermodynamic gives most stable product. Okay? Kinetic is faster. Thermodynamic gives the most stable product. That's really the whole explanation for why is something kinetically controlled or thermodynamically controlled. Now look at this. Here's why it's faster. Do you see if this H goes in here, the X might be right by it. It might be right next to it. Let's think, you know, you might not have them distant from each other. They might be right on top of each other. Let me get another pen. Suppose we didn't draw this over an arrow, but instead we drew it like that. Wow, they're right next to each other. So they're very fast. These electrons hit that, and then as soon as these electrons hit that, these electrons go here, and that becomes a carbocation, and boom, it's all right there. Very fast. Okay? That's kinetic. Alright? Now, thermodynamic, though, is going to give the more stable product in the end. How many substituents does this double bond have? How many non-hydrogens does this double bond have? Only one, right? How many substituents does this double bond have? It's got 2. Okay? So the more substituted double bond, more substituted alkene is more stable. Why? Why is that? Because the Hammond postulate, which says that alkyl groups are, boom, you finish that sentence for our meeting. Okay, best wishes. Hopefully this is helpful. That's lesson 4.